Well, hi everyone. In this video, I'd like to talk a little bit about one of the powerful reasons that uniform continuity is important in real analysis. Remember that uniform continuity is kind of a strong version of regular continuity, and I've reminded you here of the definition of uniform continuity. Remember first and foremost that uniform continuity is a concept that is applied on an entire domain D of your function f. So when we talk about regular continuity, we can talk about continuity at an individual point, at a point C, which is part of the domain of the function. However, when we're speaking about uniform continuity, we're talking about continuity that extends to an entire domain, an entire sea of points, right? And so that's what I'm calling D here. So if we have a function f defined from D to R, it will be uniformly continuous on D, right? Emphasis on D, right? If for all epsilon greater than 0, there exists a delta greater than 0, such that for all points, I'm going to call them x and y in the domain D, if the absolute value of x minus y is less than delta, then the absolute value of f of x minus f of y is less than epsilon. The point being that this choice of delta should not depend on what x and y are. Notice that we are supposed to find the existence of this delta before we specify which points x and y we're going to use. And in fact, this is supposed to be a delta that will work for all x and y throughout the domain. And that's the sense in which uniform continuity is a stronger definition than just a function being regular, continuous. So remember that we had a number of theorems that applied to continuous functions. So again, that would be continuity point by point. At any point C, we can talk about a function being continuous. But if the function was continuous on a closed interval, remember that we had a number of really well-known results. We had the extreme value theorem, boundedness of continuous functions, the intermediate value theorem, location of roots, and so on. But if you remember, in all of those theorems, the function f needed to be defined on a closed interval, AB. If the interval was not closed, however, those results don't apply. Well, one of the important applications of uniform continuity, and I'm going to make this note here, a major application of uniform continuity is that we can extend a continuous function. Let's say f, which is defined on an open interval AB to R, we can extend that function to A and B so that f is at least continuous on the closed interval AB. Okay, so maybe our function is not currently continuous on a closed interval AB. In fact, maybe it's not even defined on a closed interval AB. Maybe it's only defined on an open interval AB. Well, if your function was actually uniformly continuous on that open interval, you can actually extend it in a continuous fashion to the endpoints A and B. So I'm just going to say we can extend a continuous function to A and B so that the function remains continuous on the closed interval, provided f is uniformly continuous on at least the open interval AB. So if it has this sort of strong flavor of continuity on the open interval, then we can extend it to the closed interval. And at that point, we don't really need it to be uniformly continuous anymore, because if f is continuous on a closed interval AB, then all of those previous calculus applications that I just mentioned can be applied. So this is really a reason to care about uniform continuity. Why is it important? And let's actually state this as a theorem. If you're following along in Dengello and Seyfried's Introductory Real Analysis book, you will find this as theorem 4.7. And so I'm going to state it right here. If f defined on the open interval AB to R is uniformly continuous, on that open interval AB, okay, then f can be extended. F can be extended to a continuous function f can be extended to a continuous function defined now on the closed interval AB to R. So of course, to prove this, which is the main thing I'm going to do in this video, we would need to prove the extension at both A and at B. But if you look in that Dengello and Seyfried text, they present the proof for how to write it up when you're extending to A. And so what I'm going to do here in my proof is I'm going to focus on the extension to B. So I'm going to just show you how to extend F. By extend F, what I mean is define F at B. I'm going to tell you what F of B is in such a way that the function will still be continuous even at B. It's already uniformly continuous throughout the open interval. I just want to confirm that it will be continuous at B, or that it's possible to define F of B in such a way that it will be continuous at B. Well, here's the first thing to note about this. I'm going to kind of, instead of starting from the beginning, I'm going to sort of give you the big picture of the proof here. The way that I'm going to extend F so that it will be continuous at B is I'm going to simply prove, so we will prove that the limit as x approaches B of f of x exists in R. So it's not plus infinity, it's not minus infinity. We're going to prove that this limit exists in the real numbers. It actually has a real number value. And if so, why is that the main crux of the proof? Well, because if so, then what we're going to do is we will define, remember our goal here, guys, is to define what f of b is. We have to show that we can continuously extend f to be defined at b. So how are we going to do it? Well, we're going to do it exactly by defining f of b to be whatever this limit is. We're going to define it to be the limit of f of x as x approaches b, which if it exists as a real number, then this will make sense. F of b will be a real number, which is of course what it would need to be if we're defining a value for f of b. Okay, so that's the whole ball of wax of this proof, is to simply show that the limit of f of x exists. And somehow we're going to use the fact that f was uniformly continuous on the open interval AB to do it, because that's our assumption, right? But as soon as I define f of b in this manner, by the way, let's just remember that that will make f continuous at b, right? Remember this huge remark that we sometimes talk about, right? That one way of characterizing continuity at a point is that the limit as x approaches that point of f of x should agree with the value of f at that point. This is basically the huge remark. And so we will define f of b to satisfy that remark, and it will automatically be continuous at b from there. So this is really the main crux of what we need to do. I'm going to come over to the other side here to try and focus on how are we going to prove that this limit exists. Well, in a rare move, guys, in a rare use of sequences, I'm going to use a sequences characterization of limits to do it. Normally, we don't prove that limits exist by using sequences. Normally, we disprove that limits exist by using sequences. You might remember that sequences were a powerful tool for disproving continuity. But in this proof, we're actually going to use sequences to prove that this limit does exist. What we have to do is take an arbitrary sequence that converges to B to begin with. So let's do that. Let's let, I'm going to call it x sub n, be a sequence converging to B with all of these xn's in the open interval from A to B. So they have to be in the domain of the function. And of course, then if we have this sequence converging to B, then this is a Cauchy sequence. This is a Cauchy sequence. So let's just write that down. Then xn is Cauchy. And so by another theorem in D'Angelo and Seyfried's book, it's theorem 4.5. I'll state it here. I won't rewrite the whole theorem back down. But what that theorem said is that if your function is uniformly continuous on a domain, then if you take a Cauchy sequence within that domain, its image will still be Cauchy. So this is a sequence that is certainly convergent within the domain, therefore Cauchy within the domain. And so by theorem 4.5, since f is uniformly continuous, and now this is exactly where we're using the assumption in this theorem 4.7, because f is uniformly continuous on that open interval AB, then the image of the sequence, which would be the sequence of f of xn's, is Cauchy. Of course, this will be Cauchy somewhere in R. It will be Cauchy somewhere in R. And if it's Cauchy in R, then it converges in R, right? So this f of xn is Cauchy in R. So there exists a limit to this sequence. Let me just call it, there exists an L, let's say, in R with the sequence of f of xn's converging to L. So we have a sequence in the real numbers that is Cauchy. It's the image of the original sequence. And so f of xn is going to converge to L. And my claim is going to be that when we're proving down here, remember what we're trying to prove, that this limit of f of x exists? Well, I'm going to actually claim that that limit as x approaches b of f of x is actually equal to this number L, whatever it was. So this L makes an appearance in the proof as the limit of this Cauchy sequence in R, and the claim is going to be that that is actually the right number L to make this proof run, right? We're going to prove that this limit exists in R by proving that it equals L. That's how it works. Feel free to pause, to slow down, to rewind, rewatch, or jot down questions for me. If anything that I'm saying along the way here is not clear, I will be glad to do that. Okay, well, again, to prove this claim, I am going to use sequences, okay? But not the original sequence of xn's. Okay, so the xn sequence is already here, but now I have a fresh claim in front of me, and I'm going to prove this claim by using sequences. Let's just call this a little proof within the proof now. And the way this is going to work is we're going to take a sequence, I'm going to call it y sub n, that converges to b, and y sub n, remember when we're taking limits as x approaches a point, then we don't really care what's happening at that point. So I'm not going to allow a y sub n to be equal to b for any of these n's. But we take a sequence that converges to b, and this is an arbitrary sequence. Okay, so that has to be an arbitrary sequence. And of course, this is going to sound like deja vu. This is a convergent sequence, therefore it's Cauchy, and therefore the image of it under F will still be Cauchy again. Okay, so we're going to run through all of that again. So since Yn converges, Yn is Cauchy, And so the image of that sequence is still Cauchy in R, by the way. The image of the sequence is Cauchy in R by theorem 4.5. So I'm using that same result out of D'Angelo and Seyfried's book that says that for uniformly continuous functions, the image of a Cauchy sequence is still Cauchy. Okay, great. So the image sequence is Cauchy and hence converges. So hence there exists what I will call L1 in R with the sequence of f of yn converging to L1. Okay, what do I actually need to prove? What I actually need to prove for this claim is that, so to prove that the limit of f of x is equal to L, I take an arbitrary sequence that converges to B. I have to show that the image of that sequence converges to L. And we don't know that yet. We don't know that yet. We just know that it converges to something, to some real number. I'm going to call it L1 for right now. And my goal is going to be to prove that L1 is actually the same as L. That's how this works. I know it feels a little awkward. There's this multiple sequences converging to multiple things. But in fact, this L1, which comes as the image of the original sequence of y sub n's, is going to exist, and we have started with an arbitrary sequence, okay? So we have started here with this arbitrary sequence L1. Okay, so that what we need to show, in other words, what I just got done saying, is that we need to show that L1 is the same as L. If we can prove that, we are done. So here is the trick, and this is kind of an interesting little trick here. We are going to make a new sequence, which I am going to call Zn, which is obtained by staggering the terms of the two sequences we already have created. Namely, we have the xn sequence and the yn sequence, and I am going to make a new sequence x1, y1, x2, y2, x3, y3, and so on. Now, you may remember that there's an easy exercise involving sequences, that if you interlace two sequences that both converge, and by the way, they're both converging to the same thing. So xn converges to b, yn converges to b. So then we can say that zn also converges to b. This is a homework exercise in D'Angelo and Seyfried's Introductory Real Analysis book. And it's just in the sequences chapter, kind of a standard problem involving the definition of convergent sequences. So the Zn sequence is going to converge to B. And so one more time, guys, if the Zn sequence converges, that means it's Cauchy, which means the image of it is Cauchy, which means in R, which means that the image of this sequence converges in R. I'm going to say that it converges to M for some M. Okay, so this is actually already the third time we've kind of run that same reasoning, right? What is the reasoning again? Your sequence converges. Therefore, because F was uniformly continuous, the image of the sequence will also converge. And we do that by pointing out that convergent sequences are Cauchy, and the image of a Cauchy sequence is still Cauchy under a uniformly continuous function. And Cauchy sequences converge. Okay, so the f of Zn converges to M for some M, and every subsequence of a convergent sequence has to converge to the same value, right? So here is so what is this sequence, by the way? So f of Zn, just to be totally clear about what it is, this is the sequence x of x1, f of y1, f of x2, f of y2, f of x3, and so on, right? That's what that sequence is, and it's converging to M. It's converging to M right here. And so every subsequence converges to M, right? So the subsequence of the odd terms, which is the f of xn's, right? That has to converge to M. And the subsequence of the even terms, which is the f of yn's, that also has to converge to m. Well, if you now just look at what we've said, right? F of xn was supposed to converge to L. F of yn was supposed to converge to L1. Turns out they're both equal to m, the same value m. So thus, L1 is the same as m, which is the same as L. And so that concludes our proof in this case. Whew, takes a little bit of work, doesn't it? So just again, quick reminder, what we did is we came up with this real number L, and we claimed that the limit of f of x as x approaches b was going to be equal to that value L. And if it is, then we're just going to define f of b to be equal to L, right? So that L value is the magic value that we're going to use to extend f to b. So we do that by making this claim that the limit as x approaches b of f of x is equal to L. And the proof of it is a little bit unexpected. We use sequences to do it. So we create a sequence in the domain, the y sub n's converging to b. And what we have to do is prove that the f of y-n's will always converge to that same L, regardless of what this arbitrary sequence is. So we first just prove that it converges. We don't know that it converges to L, but we do manage to conclude that f of yn converges to something. So I called it L1. And then the bottom half of my board over here is where we actually just show that L1 is the same as L, so that it's not some other limit value. It is actually L. And this creating this staggered sequences of the xn's andyn's is really the sneaky way that we are able to accomplish that. So, a really powerful reason to care about a uniformly continuous function. If it's defined on an open interval, you can extend it to the endpoints in such a way that the function is still continuous, but now it's defined on a closed interval. And as such, it is ripe for applications of the intermediate value theorem, the extreme value theorem, and many other results in calculus that I'm sure you're well aware of that are really quite important. So thank you for taking the time to watch this little discussion of this result. It's an important one, but the proof is a little bit interesting. It takes a little bit of cleverness. So I hope that it makes sense. Be sure to ask me if you have any questions about it, but I hope it makes sense for now. And thank you so much for taking the time to watch this. I'll see you all again soon. Bye for now.